Well, we've finished our talk about free undamped motion, which is not as realistic as what we're going to talk about right now. Free damped motion. Undamped motion means there's absolutely no friction whatsoever. Your spring mass system is just going to continue doing the same thing forever. Free motion means that there's no external force, causing it to go forever and ever. So we're going to talk about free damped motion. Damping forces, like a dash pot on a door, the things that prevents the door from slamming, or if you were to place your spring mass system into a pool of water, now you have the friction of the water, or some other viscous liquid honey or syrup or something like that. Damping forces are assumed to be proportional to velocity, and you can feel that in your swimming pool. If you move your hand, the faster you move it, the more you feel that resistance of the water. If you're not moving it at all, you don't feel the resistance. Okay, so we have this differential equation. Well, the one we used to have was this. That's what we started with the undamped. This term is being added now for the damped motion. And notice that beta is a constant that is multiplied by the velocity, because damping is proportional to the velocity. Beta is called the damping constant, and it's a force opposite of motion. This may not be the way we normally look at it. We'll usually put it all on one side, and we'll see it that way in just a minute. Okay. FDM, free damped motion, giving you the solution to the ordinary differential equation that corresponds to this right here, this homogeneous equation. This differential equation, the equals 0 means it's a free system. It's not there's no force that's going to keep this thing going on forever. So we moved everything to one side and we changed a couple of the letters. Beta disappeared. The mass wasn't here at the beginning. So this is kind of the form we're going to want it to be in. Get the coefficient of the second derivative just to be a 1. And we'll define what the lambda is and so on. Omega squared, I think we remember what that is. Okay, so the ODE for free damped motion is this, where omega is the square root of, remember K is the spring constant, and M is the mass of the object at the end of the spring. So that didn't change. Now 2 lambda is equal to beta over M, where beta is the constant associated with the damping constant. And you can see where that came from. If you had a beta here, and you had M here, you'd end up dividing by M. And using 2 lambda just makes things work out better with the algebra. So this number right here is beta divided by M. Here's the solution, and I just need to define this before I do the solution. D is equal to the square root of lambda squared, here's lambda, minus omega squared. That looks a little bit like the determinant in the quadratic formula, and that's where it came from, and that's why we're using D. So, we have 3 cases. That'll sound familiar because we can have the discriminant being greater than 0. It can be equal to 0 or it can be less than 0. And these should look fairly familiar other than the fact that we're now using a lambda and the capital D. So if the discriminant is greater than 0, then this is the position, this is the solution. E to the negative lambda t times C1 e to the radical d times t plus C2 e to the negative radical d times t. And we'll go back and discuss the distinction between among these three cases in a minute. When d is equal to 0, x of t is just this, c1 plus c2t times e to the negative lambda t. And when d is less than 0, we've got x of t equal to e to the negative lambda t times this. This is the only one that has sines and cosines in it. c1 cosine of radical d times t plus c2 sine of radical d times t. And in all three of these conditions, it's going to approach a steady state. It may never get there, but it's going to approach it. Now let's go back and think, what's another word for, let's see, if we're thinking about the quadratic formula, if the discriminant is bigger than 0, that means we're going to get real roots, and we're going to get two distinct real roots. So this is the first one is two distinct real roots. And the discriminant, when the discriminant is 0, that means you only get one root, and it's a real number. So this is one, I'm going to say repeated root. In other words, that polynomial would be a perfect square. One real number that just repeats twice. And finally, a negative number on the radical means that you've got complex numbers, which would be a complex conjugate pair, something like a plus or minus bi. So I will say two complex roots. And let's kind of explain where this comes from. Well, this is the differential equation in question. What would be the characteristic equation? It's a homogeneous case, so we've got m squared, because the coefficient is 1 in front of that, plus 2 lambda times m plus omega squared equals 0. So all we need to do is the quadratic formula and see what we get. We would get the solution to this. The two zeros would be negative b, which is negative 2 lambda, plus or minus. Then we get b squared, which I'll write as 2 lambda in parentheses squared, minus 4ac, which would be minus 4 omega squared. All over 2a, which is just 2. So what does that give us? That gives us negative 2 lambda over 2, which is a negative lambda, plus or minus. Well, why did I write 1 that way when I didn't write the other one? I'm going to write this as 2 omega squared, maybe. Now let's use 4 lambda squared minus 4 omega squared. That's b squared minus 4ac. So the square root of that is going to give us, I'm going to factor out the 4. I can factor the 4 out of that and make it a 2 lambda squared minus omega squared over 2. And sure enough, the 2's cancel out. And we get negative lambda. I'm not going to write it over there. You can. Negative lambda plus or minus radical lambda squared minus omega squared. And that's where this comes from. So D was simply the discriminant of the solution of this quadratic equation, the characteristic equation. Okay, one more thing. The terms for these, maybe I'll use a different color here. There are 3 terms for these. This one is called overdamped. When D is great, when the discriminant is greater than 0, and you get 2 distinct real roots. So let me go in order. What does that look like? Overdamped. Well, it means that if it's a dash pot on the door, overdamped means it's damped so much that it almost never closes. So it's going to be something like this. You know, it's just going to take a long time to get to the closed state if we're talking about a door. So this would be overdamped. And the next one we're going to look at is, the next case is actually the good case, number 2. This is probably the most desired. It's critically damped. So critically damped, I don't know if you'll be able to see this, but I'm going to put a line separating these so we know what comments are with which. These two are together, and then these two are, well, these 3 lines are together. Critically damped is good. It gets it very close to the equilibrium state very quickly. So it's not going to go, if the door opens up and closes both directions, it's not going to go like this, back and forth, back and forth. It's just going to get it to the closed state very quickly. Now, graphically, for the critically damped, it's going to go very quickly towards that and then smooth out. Now, there is one other possibility with critically damped. It could cross the barrier one time. That's interesting, that it will not oscillate though. It could go, I'll use a different color here, I'll use red. It could go down like this. Like that. But either way, it gets close to that equilibrium very quickly. Now, is the most desirable case, I would say in applications. Last one is, let's see, we did overdamped, critically damped, underdamped. Underdamped case means it's not damped enough. It goes past the equilibrium and then goes past it again the other direction, back and forth, back and forth. And I might need a little bit of extra space on this one. I'm going to raise it up just an inch or 2. Because notice that this has e to the negative lambda t. Well, assuming lambda is a positive number and negative lambda is negative, obviously, then I'm not going to draw this graph, but we draw, that's something like what an e to the negative t graph would look like. And then from the bottom, it would look like that. What this does is oscillate but stays within those bounds. So, it may start up or down. You don't know where it's going to start here, but it could go like this. Like that. That is underdamped. In physical models, that's not desirable typically to have it just swinging back and forth and taking forever to kind of get closer to the equilibrium state. So we've got the 3 cases: overdamped, 2 distinct roots; critically damped, 1 repeated root; and I didn't write it in, but underdamped is this one. And I'll go ahead and draw a line just to separate those 2. So we get the right comments with the right equation. So that's the introduction to free damped motion.